So I think you can see my slides and can also hear me, right? So if everything is clear, then I can start the session, and I welcome you all to the live interactive session. So this is an extra session on the NPTEL course, Introduction to Electrical Engineering by Professor Bhim Singh. And as you know, I will be your TA for this session. So this is a brief bio about me. And in this session, actually, we are covering various types of systems, that is the transformers and as well as the synchronous machine, the induction machine, all kinds of problems we'll discuss. And this live extra session is actually kept to actually be a little inclined towards your doubts, so that you can interact with me and can clear your doubts. That is the whole purpose of this extra session, okay? As well as we will solve many problems related to individual subjects, right? The transformers, as well as the induction machine, the synchronous machine, the mutual coupled coils. So you can ask me any of your doubts in the whole course in this session, and can stop me and ask me anywhere, right? And I prefer that you just unmute and speak up so that I can understand where you are getting the doubts, so that I can clear them for you. Else the session flow will proceed as the mutual coupled coils, then we'll take up the transformers, then the induction machine, and then the synchronous machine, right? So that will cover almost a large part of the course, because I thought that in network theory we have already discussed a lot of problems, but in machines we need to discuss more. So transformers, then coupled coils, then induction machine and synchronous machine, I have kept some problems, but just feel free to ask your doubts from anywhere in the course, right? So that I can just clear your doubts. Otherwise, you just solve the problems that we are keeping on the screen, and then that will also help you for a revision, right? So main purpose is for a revision of the machines part. So any doubt up to the course that you have studied, up to the sessions? I think you have already seen all the sessions, right? All the 12-week sessions, and by this time I think you will be revising for your exams on 27th. So if you have any doubts, let me know. So because this session is meant for doubts actually. If you have any doubts, let me know. You can just unmute and say, okay, please feel free to discuss, because these are interactive sessions, right? So you can just unmute and speak. So do you have any doubts? Okay, so if there are no doubts, just feel free to stop me anywhere within the session. Else we'll go to first the mutually coupled coils. We have discussed them in the session, but I felt more problem solving is required, right? So the first problem is on your screen, and I hope you can solve it. Just give it a try. I think the problem is visible, right? Yes. So just see and give it a try, then we'll solve, okay? So the first problem is relatively easy, right? Because it's just a brush up of your concepts, because L1 is given to be 0.5 Henry and L2 is given to be 0.4 Henry, and coupling factor K is also given to you to be 0.8. And as you know, the formula of mutual inductance between two coupled coils is given by K root L1 L2. Here if you plug in 0.8 and L1 L2, you will get it as M as around 1.13 Henry. Just check the answer, okay? And why we need M? Because it is asking us to calculate because these two coils are coupled and I pass the current in the coil, then voltage will be induced in the other coil, right? So what is V2? V2 is M times dI1. Then if you plug in 1.13 ddt times 20 sine 314 into T, this is the current and this is a time varying current, so the amplitude of voltage can be found out from here. So V2 will come out to be 7.1 kV. This is the RMS value, right? Why? Because if you differentiate V2, what you will get? 1.13 into 20 into 314 into cos 314t. So if you try to determine, this is the peak value, right? So what is the peak value? So let us calculate, okay? 1.13 times 20 times 314. So this is the peak value, right? So RMS will be, this is the peak value, and so this is the maximum value of the inductance in induced voltage actually. So this is the V2 max, I can say, peak value, not the RMS value, okay? So these can be found out from here. And please note also we have discussed similar concepts like if both currents are entering into dot, then take M as positive. Positive where? In the KVL equation. How to write the KVL equation for coil 1? If I give V1, then I can write V1 equal to L1 dI1 dt plus, because of this case, M dI2 dt. Similarly, V2 is like this, L2 dI2 dt, this is the self plus mutual. So self plus mutual plus M, because M12 and M21 are same, we already have seen that, M dI1 dt. So for 2 it is 1, okay, because of the coupling. And then accordingly you take the sign. So this is as per this rule. If both the currents are entering the dot, in that case M is positive. So if someone gives you like this, I2 in this direction, but the dots are like this. So you see, I1 is also entering the dot, I2 is also entering the dot. So in this case also, M is positive as written in the KVL equations, right? So this is how you solve the problems. And if they ask you simply the value of the voltage, you just, because of the terms M, I can apply. Because of the tightly coupled coils and there are no other values, so you can just see the self term is very less and the almost it is the mutual term. So you can just find out the voltage, right? Okay, so if there is no more doubts, I think we can proceed to the next problem. So next problem gives you 4 coupled coils having inductances, the self inductances as 1 millihenry of all the coils, but the coupling among the coils are given. So if I try to write them mathematically, L1 equal to L2 equal to L3 equal to L4 equal to 1 millihenry, it is given. Now mutual inductance, that is the coupling between coil 1 and 2, coil 2 and 3, coil 3 and 4, and coil 1 and 4, and coil, I can say, 1 and 3, as well as coil 2 and 4. Right. So I can see 1, 2, 3, 4, 5, 6. Yes. Okay. So M12, as I can see, 1 and 2 is 4 millihenry. And M23 I can see is 1 millihenry. So M12 4 millihenry, M23 is 1 millihenry. Then comes M34. M3 and 4 are coupled with 1 millihenry. 4 and 2 I can say is the violet one, which is 5 millihenry. 1 and 3 is the grey color one, which is 2 millihenry, and 1 and 4, which is the yellow color one, is the 6 millihenry. Now, how to select the sign? Select, I can say, sign. So I told you, if current enters dot in one coil and also enters the dot in other coil, then take M as positive. So let me see, if I pass the test current here, then coil 1 it is entering, as well as coil 2 it is entering. So the mutual inductance between 1 and 2 can be taken as positive, right? Just give a thought over it. So I think you understood the problem and hope you have solved it also, because then you can see that I can plug in the symbols. So 1 and 2 I can say positive because current entering in both the dots for 1 and 2. For 2 and 3 I can say if one current is entering the dot, other current is leaving the dot. So they are negative. Then 3 and 4, if current is entering the dot and again entering the dot. So here you can see current is leaving the dot and entering the dot. So how to see whether it is leaving the dot or entering the dot? Just see the coil, and if I say the dot is here, then obviously each coil is completely traveled. After that the current will be considered leaving the coil from here. Okay. Then this coil has started just. So the dot is here. So if current flows like this, I will consider it to be entering the dot because the dot is at the starting of the coil and the current is entering the dot. So one is leaving the dot, one is entering the dot. So 3 and 4 is also negative. Okay. Now try for the other ones. So 1 and 4, how will it be? 1 is also entering, 4 is also entering. So 1 and 4 is positive. 1 and 3, how will it be? 1 is entering but 3 is leaving, so it will be negative. 2 and 4, how will it be? 2 is entering but 4 is also entering. So I can say it is positive. So what is the formula of LEQ? L equivalent. It is L1 plus L2 plus L3 plus L4. That is the self and in series connection plus now the mutual. 2 times M12 plus M23 plus M34 plus M14 plus M13 plus M23 with the signs. Put value with sign. Okay. Put and tell me how much is it coming. So if I write, I can tell that LEQ is 4 because 1 plus 1 plus 1 plus 1 plus 2 into M12 is 4 minus 1 plus 6 minus 2 plus 5. This is the total millihenry, right? So it will be coming as, let me do 4 minus 1 minus 1. So 6 plus 4 is 10 minus 2 is 8 minus 2 is 6, 11, 22 plus 4. So 26 millihenry, right? LEQ. And another information I just want to give you for parallel connected coils. For parallel connected coils, just try to find out the equivalent inductance. So what I mean is that if two coils are like this and I want to find out the equivalent inductance, right? So what will it be? It will be L1 L2 minus M square divided by L1 plus L2 plus minus plus 2M. So this minus plus is actually same rule, but it is actually, you can write it like this. So minus when current, so note it is opposite here, right? And plus when current enters and leaves other. So just give a brief overview and see how the formula is working. So, or in other words, for aiding, I can say this is the one, and for opposing, I can say this is the one. So, how does the opposing will look like? Is the current, and this is I1 and this is I2. So you see, it is entering and it is leaving. So opposing. This is opposing. Put M plus in formula. And this is since current is entering, put M minus in formula. So this is a little bit opposite. Only in this place you need to put the signs, right? So this is aiding. Hope it is clear, right? And they are also asking you to calculate mutual inductance for two ideal coupled coils. So for ideal coupled coils, take coupling factor K equal to 1. So it gives us M is 1 times root 4 into 8, or it is coming around root over 32, which is 5.66 Henry. So this is the answer. Please let me know if there are any doubts, else I will just proceed with the other problems, right? Because this is easy, and if you can understand these concepts and how the signs are taken and how the inductances are calculated, then you don't have any problem solving such numericals, right? Then we'll go to transformers. Just a brief overview. We have touched also in the previous sessions, and then we'll see some more numericals on single phase transformers, right? And if you have any doubt, you can just let me know, or else I will proceed, right? So let's touch upon some portion of voltage regulation, right? So as you understand, I have a equivalent circuit of a transformer, and if I see it from the secondary side, then I can write, because this side is the loads are connected, right? So R1 dash X1 dash, and then I can write R2 X2, and this side is called as V2, this side is known as E2, so loads connected at secondary terminals, and we see the voltage regulation with respect to the secondary, right? And then how can we define the voltage regulation? Obviously in terms of percentage as E2 minus V2 by V2, simply mod of this times 100%, and obviously this is your I2. So this is neglecting high impedance parallel magnetizing branch. And then if we draw the phasor diagram, you can see that if this is V2 and I get a lagging power factor at the load end, right, which is of, let's say, theta, then V2 plus this drops, so I can say I2 are equivalent to, and then J I2 X equivalent to, if all these are X equivalent or R equivalent, we can write, then this much is the actual E2. So the voltage regulation talks about this length minus this length compared to this length, and then divided by 100%, multiplied by 100%. So simple as that. But then to simplify things, we apply some more geometry, both for lagging and leading cases, and we try to simplify the formula for voltage regulation as per the loads, right? Whether it is operating in full load or not, as well as whether it is operating in lagging or leading, we have some formulas for them. So we can touch upon those and see how the phasor diagram is working for both lagging and leading power factor, right? So you try to draw a phasor diagram to show the variation of terminal voltage V2 for first case is lagging power factor loads. This is case 1, right? And case 2 I will give you also. Draw a phasor diagram to show the variation of terminal voltage for leading power factor loads. Obviously with respect to secondary, right? Because loads are connected, I assume that I excite from the primary side and I take out the loads or power the load from the secondary. That is based on the nomenclature, right? So try to draw the phasor diagram and derive a formula for voltage regulation, because from the phasor diagram only we'll derive the voltage regulation formula, right? So I'll give you some time, you try and then we'll see, okay? So I hope you have tried and found something. So let us see how it will happen. So I change the color, I think. So let us, for example, this is V2, right? And I told you it is operating at lagging power factor. So let us take this as I2 and this is theta 2, right? The operating power factor. And for example, this is I2 RE2 and JI2 XE2, right? And obviously this is E2. So if you see and try to find out some geometrical relation. So if I call this point O, this point A, maybe this point as B, this point as C, I can write OA plus AB plus BC is nothing but OC. Let this point be D. Now OC and OD can almost be assumed same if this delta is very small. And it is true. Why? Because RE2 and XE2 are small. That's why we can assume this delta to be very small. And if so, then OD and OC are also very small. So OD is what? E2. E2 can be assumed to be OC. And OC is what? This OA plus AB plus BC. And what are OA plus AB plus BC? You can write it as V2 lengthwise I am telling, plus AB is I2 RE2 cos theta 2 plus BC. So this angle is also theta 2. So BC can be written as sine theta 2, right? So I can write it as I2 XE2 sine theta 2. So these are all lengths, right? So what is E2 minus V2? As per the definition of voltage regulation, it is nothing but I2 RE2 cos theta 2 plus I2 XE2 sine theta 2. So there is a plus coming for lagging, right? But there is by V2 also. So just incorporate that and then multiply by 100%. So plus for lagging, remember, okay, in the formula it is coming as a plus sign geometrically. We have derived it. So for lagging power factor, your voltage regulation is coming positive, right? Let's draw for leading power factor. Similarly, we have V2. But now the leading power factor, right? So let's say this is I2, this is I2 RE2, and then we have JI2 XE2, which is 90 degree, right? And this will give you the value of E2. Just generally seeing, you can understand that V2 is greater than E2 and implies a negative voltage regulation, which implies this only, right? That the length of the terminal voltage vector or phasor, you can say, is more. That is a general notion for a leading power factor operation, right? Which is theta 2. And then you can understand that I can write it like, if I draw like this. So how can I write it? This is B. So OA plus AB then minus this BC will give you the length of OC, which is almost equal to OD, as I told you, due to the angle being small, due to small RD2 and XE2. So I can write E2 being almost equal to, because OD is E2 and OA is V2, so sorry, OC is V2, so OC OA is V2, right? Sorry, this much will be V2. So OA is up to this much, right? So V2 plus AB is I2 RE2 cos theta 2 minus I2 XE2 sin theta 2, only the length, right? So what is E2 minus V2 by V2, right? It's coming as I2 RE2 cos theta 2 minus I2 XE2 sin theta 2, and then you divide by V2 multiplied by 100%, right? So this is the formula where we see a negative sign indicating negative voltage regulation for leading power factor, and the negative sign just implies that V2 is greater than E2 for certain leading power factor operation. But you understand that we can get zero voltage regulation also possible. It is not possible for lagging power factor operation, but it is possible for leading power factor operation. And just by equating it to 0, you can calculate the power factor. So I give you as a homework, calculate power factor, that is obviously lead, for 0 voltage regulation. This you can do as a homework. Just put this term as 0 and calculate the power factor by drawing the impedance triangle. I hope you understand how to draw and how to determine, right? That will be a good exercise, and I hope you can do it yourself, and I can refer also many standard books or the lecture also. It is given clearly. So you can do that, and it will be helpful for solving the numericals. So do two things. For 0 voltage regulation, calculate the power factor, and calculate the power factor also for maximum voltage regulation, right? So you can do these two things, and next you can try this problem. So I will give you some time, just see this problem, right, on the single phase transformers. So I hope you have tried the problem and you know also that how to draw the phasor diagram, right? Because in such kind of problems the phasor diagrams help actually. So if this is the flux, then V1 I will take like this 90-degree lead. Obviously E1 will be 90-degree lag, but I take E1 like this, and then the I naught, which is of a higher angle because of a poor power factor, because it is only the magnetizing branch. So this is I naught, and with that I add maybe the I2 dash, which is nothing but reflected as I1, and it will lead to I1 dash, right? So I1 and I2 dash are same, right? And I1 plus I0 is nothing but I1 dash. I name like this. So this is the secondary power factor, right? And this is the primary power factor. And I can also name this as phi 0, which is the no load power factor, which is poor, right? Because of the magnetizing branch only being activated. So now you see it has given us the number of turns. There is a turns ratio. So number of turns on primary is N1 and secondary is 200. And the no load current is given as 3 ampere at 0.2 lagging power factor. Then they are asking us to calculate total primary current. So total primary current I1 dash is known as I0 plus I1. And we know that secondary is loaded with a current. So I2 is given as 280 at 0.8 power factor lag. So if I try to take everything with respect to the primary, right? Primary. So I2 referred to primary as I2 dash or I1 can be written as I2 into 200 by 1000, because on the higher turn side the current will reduce, right? Like that. So how much is it coming? It is coming around 56 ampere, right? So this is the RMS value. But this current has a power factor of 0.8, as you can understand. So I0 is nothing but 3 ampere RMS at 0.2 power factor lag, and the sum of these two, I1 plus I0, but the phasor sum will give you I1 dash or net. So how can we write that? It is nothing but 56 at an angle of minus some theta, which is cos inverse 0.8, plus 3 at an angle of minus cos inverse 0.2. So if you do that, you'll get a lagging power factor for sure, and we do the phasor summation, you will get it. I1 dash net is coming as 58.3 at an angle of minus 38.5 degree. So do this cos inverse 0.8 and take it to the degree, and then do it, you will get it as the answer, right? So this problem was nothing but to take the secondary current with respect to the primary and then add it with the no load current to get the net current, right? Simple. It is asking you to calculate the net current, and the power factor becomes cos 38.5, which is theta 1, I can say, operating power factor of the primary side, which is nothing but 0.78 lagging, right? So this drop in or reduction in power factor from 0.8 is due to the no load current, right? Which is a point of observation. Please observe that since you had the no load current, it pulled it slightly, it pulled the, I can say, power factor to the poorer side or the lower side slightly, and the overall current power factor slightly degraded to 0.78 lag. Otherwise it was 0.8 lag, right? So hope with this you have some understanding that how the no load current can also play into role, that the no load current will be decided by the voltage, and then it also has a factor taking into account the drop in the windings. So you calculated the drop in the windings, and they have been already given to you as the form of, in the form of current, that how much current is being drawn, and accordingly based on the principle of operation of the transformer, you just reflect the current in the secondary and then add it with the no load current, because the current values are already given, so you do not determine them again using the parameter values as they have not been furnished. So use the currents and just add them to get the net current and the power factor on the primary side, right? So do everything in terms of primary. That was the whole concern, right? So now see the second problem on your screen. So there are two parts, and the second part have two subparts, right? So try to do the first part, which is easy, and tries to understand your concept regarding the reflection of the impedances on the primary and secondary sides, right? That is easy. And I want you to try the problem, right? Just try, I'll give you some time. So I hope you have tried the problem, and if you are able to solve the problem, then it is very good. So what it is given is that we have the transformer which has 400 turns on the primary side and 80 turns on the secondary side. And they have given you the primary resistances. And then you have the coupling branch. This is the equivalent circuit of the transformer, right? So you have to reflect. If you want to reflect to the primary, then I write it like R2 dash and X2 dash and R1 and X1. So R1 is given as 0.3 ohm and X1 is given as 1.1 ohm. But R2 and X2 are given as 0.01 ohm and 0.035 ohm. So I need to calculate R2 dash, which is nothing but 0.01 multiplied by turns ratio square. And X2 dash is similarly calculated as 0.035 times turns ratio square. And R equivalent is nothing but R1 plus R2 dash, I can write, and X equivalent is nothing but X1 plus X2 dash. So we'll calculate and get it as 0.55 ohms and this as 1.975 ohms. So using R equivalent and X equivalent, you calculate Z equivalent reflected or referred to primary as square root over R equivalent square plus X equivalent square whole root over, and you get it as 0.55 whole square plus 1.975 whole square whole root over. This is calculated as 2.05 ohms. So this is the equivalent impedance referred to primary side, right? And this is the answer of part A. Now what they are asking is that the voltage regulation of the secondary terminal at full load having a power factor of 0.8 lag and 0.8 lead. So we have already determined the formula for voltage regulation, and using that try to determine the voltage regulation of the secondary terminal for a full load having a power factor of 0.8 lag and 0.8 lead. Just try it, okay? So I give you some time, kindly try it, okay? Okay, so now we come to the voltage regulation part. Now, what is the formula of voltage regulation? As you understand, we have I2 RE2 cos theta 2 plus XE2 sin theta 2 divided by V2 multiplied by 100% for lagging power factor, and similarly voltage regulation is I2 RE2 cos theta 2 plus XE2 sin theta 2, no sorry, it will be minus, please note, divided by V2 multiplied by 100% for leading power factor, right? So now let's calculate for full load at secondary terminal, that is full load current at secondary terminal. So how you calculate full load current? It is just the kVA of the transformer, which is 100 into 10 to the power 3 and divided by the voltage, RMS voltage. So what is the RMS voltage? So just see one thing, this is I2, so you have to take V2, or you can also take I1 and V1. Because this RE2 and XE2 you were taking with respect to the primary, please note, now you have to take with respect to the secondary. So RE2, XE2 are equivalent series impedances with respect to secondary, right? So what is the full load current at secondary terminal? It is just 2200 multiplied by 80 by 400, right? That is the voltage at the secondary and this is the current at the secondary. So you know V1 by V2 is I1 by I2. Sorry, I2 by I1, right? Equal to turns ratio. So you cannot use I1 and V1, right, instead of I2 and V2. You have to use I2 and V2 and RE2 and XE2. So try to evaluate RE2 and XE2. So it will be 80 by 400 whole square times your primary plus secondary, it is 0.01 is RE2, and XE2 will be similarly the primary one 1.1, and then you add the secondary 0.035, right? And cos theta 2 is given as 0.8, so sin theta 2 will be 0.6. And I told you V2 is nothing but secondary voltage, so it is 2200, which is the primary voltage, into 80 by 400. I2 is this at full load, so just calculate everything and plug in the values. So let me calculate. So it is coming around 227, and this is coming around 440. So 227.27 amps. And if you calculate RE2, it will be coming as 80 divided 400 whole square into 0.3 plus 0.01, so 0.022. So VR is coming as I2, which is 227 into 0.022 into 0.8 plus 0.079 into 0.6 divided by V2. V2 is coming as 440 in percentage, so 100 multiplied by this percent. So for lagging, it is coming as, let me calculate, 227 multiplied by 0.022, and then I multiply a 0.8 plus 0.079 multiplied by 0.6 divided by 440 into 100. So around 3.35 I am getting percentage wise. So another thing I want to tell you, if you wanted to keep this as RE2 and XE2, without that you could have kept it as RE1 and XE1. How you know? Then there will be a factor of turns ratio square, which will scale this current and this voltage to V1 and I1 that I was telling at the beginning. So that is also an approximate form that is possible, right? So you can use this, and doing for this also, you will get minus 1.54% as the voltage regulation, right? For zero point 0.8 power factor leading. Try this problem, the another problem that is given. So what is the full load secondary current? Is 500 kVA transformer and 400 volts on the secondary, so you get the current, full load current, right? But I also need the full load primary current. You plug in the primary voltage. So these resistances are already given, right? So let us calculate secondary copper loss at full load, right? It is full load, right? How much is it? 1250 square, that is IRMS square into R, 0.0019, this much watts. So this is around 2969 watts. Similarly, primary copper loss at full load. It will come as 45.5 square times 0.42, around 870 watts. So total I square R loss at full load is around 0.87 plus 2.9 kilowatts, which is around 3.84 kilowatts. But they have also given a core loss, right? Core loss is 2.9 kilowatts. 2.9 plus 3.84 gives us the total loss at full load as 6.74 kilowatts. Then I know that the output power at 0.8 power factor is nothing but 500 into 0.8, which is 400 kilowatts. Input power is this 400 kilowatts plus this loss. So this is coming as 6.74 kilowatts, which is 406.74 kilowatts. So I supply this much, right? Therefore the efficiency is 400 by 406.74. 98.34%, right? But they ask that for half load also. So for half load, copper loss is 1/4. So at half load, if I try to calculate, then I will do what? I will do 2.9 kilowatt core loss plus 1/4 of the full load copper loss, which is this 3.84. So what I get is 3.84 divided by 4 plus 2.9, which is 3.86 kilowatt. So the half load efficiency is nothing but 400 by 403.86 into 100%. Sorry, but half load, right? So this will also, load will also be half, right? So 200 by 203.86. So it will be 98.11%. Because the load is also now half, not full, at 0.8 power factor. So output power full load, right? This is 400. So at half load, it will be 200 kilowatts, right? At same 0.8 power factor. So this 200 kilowatts added with the loss, which is 203.86, you would divide, you get the half load efficiency as 98.11%. So these are the two answers of part A and B. Right, I hope I get a complete idea about the efficiency and the voltage regulation of the transformers, the single phase transformer. Now we move to the numericals on induction machines. So you must have seen that during the OC test we calculate VOC and IA, I can say. So what is the current that is flowing is the no load current, and you slightly go on increasing the voltages and take it to the rated, right? Like this, a curve will come, you plot the points, and you can see that you take more points here to build this kind of slope, and this is the V rated at which you take the get the rated no load current. Now if you take the slope from this point, what will it give? XM, right? As per the so sleep is almost equal to 0. So this can be assumed as open circuit, right? So almost all the current is flowing at I0. So IA equal to I0, and this is V rated. Now this is a non-linear element, right? It varies. As you can see, it is almost since the voltage is low, the saturation effects are not encountered, and it is almost linear. But here it becomes non-linear, and we have to take this value. So this value is actually calculated by the slope of this curve, and is important to determine for excitation requirements calculating the excitation requirements that you have to supply. Otherwise, the power factor of the supply will be poor, right? So in order to create some need, maybe some for operating it as some generator or some maybe some power pushing device, we can operate it using external excitation by giving it external excitation when the grid is absent or the power supply is absent, and we can use self build up of voltage if we can provide external excitation or reactive power from some passives like the capacitor banks. So that capacitor bank should actually able to compensate for this XM so that we can supply the reactive power at the rated voltage, right? The required amount of reactive power at the rated voltage. For that, we actually calculate XM so that we can compensate it using some other passives for standalone operation, right? So required for calculation of external passive requirement at rated voltage or reactive power requirement for standalone operations. Because if you don't have the power supply, who will supply the reactive power? For those cases, like self build up, but generator mode operation. You have to have the calculation, so that it is useful, right? That is how you calculate graphically, right? And you need to take more points at need. So now coming to some numericals also. Try to see the first numerical. So I think you know that torque is proportional to voltage square, right? We have explained it many times. So they are telling us that starting torque is nothing but 1/4 of the full load torque, and starting current is 4 times the full load current, and the slip is 0.03. So what we get is they are asking us to calculate the voltage required actually. So T start by T full load, I can write is 1/4, which is nothing but some turn square, because voltage square, you know, I starting by I full load whole square times slip. I hope you understand why we did like this, right? So in an induction machine, for a given slip, if you reduce the voltage, then since this is V by Z and Z is constant for a given slip, so I proportional to V, right? And since torque is proportional to V square, it is also proportional to I square. Or you can say N square I square. If a transformer based voltage is given as supply, because in that case the turns ratio will decide the voltage, so and accordingly the current. There will be no root square root sign, right? I did a mistake in the square root, that's why I was getting the wrong interpretation. So you see, if at full load sleep tends to almost zero, then this term is almost very high. So what I can write it as R2 by S whole square, and then I have a S by R2 term, right? So torque proportional to S for low slip, and torque proportional to 1 by S for high slip. So this value is coming as 4. This is turned square, and the starting torque is given as to be 1/4 of the full load torque, and we have the slip, which is 0.03. So how much is it coming in value? 1 divide 4 into 0.03 into 16, and I try to root it. So n is coming as 0.72 or 72% tapping, right? So I hope you understood what is the problem. So it is given that at 480 volts, if we give at 10 still, then it will develop 1.8 times the full load running torque. But we want TFL at start. Then the problem says how much voltage to give. So we know torque proportional to voltage square, right? So 1.8 times full load torque was being produced when 480 volts was supplied at the same sleep, right? We are not changing the sleep. Then at the same sleep, that is at starting, we want the full load torque. Then what voltage should be supplied? It should be 480 by root 1.8, which is nothing but 357.77. Now, with this voltage, what current will this voltage produce? I told you, for same sleep, for given sleep, V proportional to I. So, for 357.77 volts, I is nothing but the full load current is 30 ampere and the starting current is 6 times full load current, which is 180 ampere if given 480 volts. But now my voltage reduced. So the voltage reduced and it will have direct impact on the current, which is just a linear scaling down, right? So the current will be 357.77 into 180 divided by 480, right? 134.16. Now this is the current that it will produce. Now if the voltage is obtained by auto transformer, what will be the line current? So this voltage is being supplied by auto transformer, let's say. So a auto transformer turns ratio is V1 by V2 equal to I2 by I1. Right, this is primary line side. Similarly, this is also line. And this is motor, right? So now we know I2 is 134.16. And then we also know A as 480 divided by 357.77. The voltage is reduced, right, due to the auto transformer. So 480 divided by 357.77, which is 1.34, right? So what will be I1? Line current. Line current will be, since the voltage is higher on the line side, the current will be lower. So this will be 134.16 divided by 1.34. This is the line side. And how much will it be? 134.16 divided. So this will be around 100 ampere, right? So this is the answer of the C part. This is the answer of the B part. And this is the answer of the A part, right? And then D part, they are asking us to calculate the starting current is limited to full load by auto transformer. What will the starting torque? I give you as a homework this one, because remember one thing, if the starting current is limited, right, then you are actually limiting the voltage, right? So calculate voltage from current, get voltage, and then calculate ratios. So if starting current is 1/6 now, because it was 6 times full load current, the starting current, now it is 1/6. So voltage is also 1/6. For same slip at starting, I am saying. So voltage is 1/6. Torque is 1/6 square, right? So then you try to calculate starting torque as a percentage of full load torque. So I need the torque by the square, right? So you see T by T start, I square by I start square. I start is 6 times IFL and I want I to be IFL. So 1/6 square. But this is T start. I need it to be TFL. So T start is 1.8 times IFL. So plug it in and then get T by TFL, which is 5%. So now we come to the numericals on synchronous machine. So it is operating as a motor, right? There was some doubt in the previous week that if this is VT and it is operating as a motor, it is taking, let's say, some leading power factor current, right? Let's say IA, and then VT plus IA, we can say minus VT minus IARA minus JIAXS. Then this will be EF mod greater than VT, as you can see from diagram, and EF lags VT for motor. Then you see for leading power factor motor, it is higher, right? EF is higher. So it is overexcited, right? Then just see the next problem. So I think you remember the curves for OC and SC test. This is the field current. So this is a straight line, right? This is linear characteristics. So what they are telling is that open circuit voltage we get at 2.3 maybe amps. This field current we get 400 volt line to line RMS. So but they are giving the value for 1.5. How much is the short circuit current? 10 amp ISC. But I need for the same 2.3 amps, right? How much is the ISC? Because what is the formula for excess per phase is V phase by I phase. V phase open circuit by I phase short circuit for same field current. So this is okay. This is 400 by root 3 for field current of 2.3. But for field current of 2.3 amps, how much is my ISC? That I have to determine as the scaling of this 10 into. So ISC at 2.3 amps field current I have to determine, and 10 into 2.3 by 1.5 I am getting 15.33, right? So this 15.33 we can write, and then we get the ZPH, ZS or XS or ZS you can write, ZS phase, per phase, right? Because impedance is per phase always. So around 15.06 ohms I am getting ZS, the synchronous impedance, obviously in per phase. Next, it is an easy problem. Just recall power and torque equations for synchronous reluctance, maybe salient pole, right? Because it has both reluctance and the synchronous torques. So the power and torque equation are very similar. Remember, there is a sine 2 delta, right? So for cylindrical, XD and XS are same, and XQ is 0. So only for cylindrical, right? And XQ not 0, but XQ and XD are same, and all etc. There is no XQ there, okay? And then the torque equation is 1 by omega s, which is nothing but 2 pi n by 60 mechanical, and then you can write it as EV by XD sine delta, because torque into omega is nothing but power, and omega is omega s for synchronous machine. That's how it comes. 1 by XQ, same, right? Torque by omega only, sine 2 delta. So reluctance torque, this is the reluctance torque term. When is it max? When sine 2 delta is max, which is 1, then 2 delta is 90 degree, or delta is 45 degree. So for 45 degree, the reluctance torque becomes maximum. So reluctance torque at a maximum value at 45 degree for load angle to be 45 degree. So it was our derivation, and you can just see it. So coming to the next problem. So they are asking the relationship of voltage or the EMF induced, I can write, with respect to field current and frequency. So you know, in the EMF equation we see that it is proportional to field current and frequency, or this is phi f also. So we can write E1 by phi 1 F1 is nothing but E2 by phi 2 F2. So at 360 volts, or this is field current one, I can write it as IF1 frequency 1 and IF2 frequency 2. So for frequency 1, which is 60 hertz, and the field current to be, I can say, 3.6 ampere, and the E2, this is they are asking, and for 2.4, and as the field current 2 and the frequency 2, which is 40. Then E2 can be determined from here as 360 into 2.4 into 40 divided by 3.6 into 60. So E2 is coming as 160 volts. So this is a simple problem testing your concept and the dependencies of the induced voltage in a synchronous generator. That was only it was testing how it is related to the frequency and field current, that is the flux. So just apply this concept and get the answer. Right? It is a direct problem. Obviously here we neglected the saturation effects, right? So with this, if you don't have any doubt, I close the session and I thank you for attending the session. And there will be another session, which is the last session for the 12th week, where we will discuss the problems on electrical measurements. In the meantime, you can just post your doubts in the group and can also mail me, and we'll discuss all the remaining doubts in the last session in the week 12 of the NPTEL course that you are attending, which is Introduction to Electrical Engineering. So keep solving the problems, and I hope you will learn from this session and the problems that we have discussed. So thank you for attending the session, right? With this we end the session. Thank you.